Lesson 2.1, we're looking at rational numbers on the number line, and you'll learn how to graph rational numbers on the number line and find absolute values of rational numbers. How can you use a number line to show data? The table shows the percent change in the river depths of various rivers in Texas over a 24-hour period. You can use a number line to graph these values and compare the changes in each river. So if we graphed point 3, that'd be about there. -2, -0.8, and +0.1, 0, +0.2, getting a little crowded there, -0.4, and -2.2. And that helps us organize and order our numbers in order from least to greatest. This set of notes is going to have you guys doing a lot of writing because you need to write down natural numbers are the numbers we count with. Some books call it counting numbers, 1, 2, 3. So on a number line, the first number is 1, and it continues on forever to the right. Whole numbers, they just add one more number. So it is 0, 1, 2, 3. So 0 and all the numbers going to the right. Integers are whole numbers and their opposites. So we had 0, 1, 2, 3 going to the right of the positive numbers, as well as 0, -1, 2, -3 going to the left, the negative numbers. Another set of numbers you can display in a number line is a set of rational numbers. A rational number, word is ratio, is any number that can be written in the form a over b, like a ratio, where a and b are integers and b cannot equal 0, because division by 0 is undefined. Some examples of rational numbers are shown below. 1/2 is 1 divided by 2, -2/3, 17/5, 15 divided by -3, which happens to equal -5, but that's a rational number. -14 divided by -11. It's not simplified, but it's a rational number. 3:1, which is the same as 3, is a rational number. A rational number can also be expressed as a decimal that terminates, which means ends, or as a decimal that repeats indefinitely. And for the repeaters, we use the bar. We're used to that for -1/3. I just wrote over my bar. Or we're used to 0.5, 3.4, 2.6767. They could have put the bar over the 6, 7 because that's where it's repeating. -5, it terminated. It's also an integer, but it's a rational number too. 1.27 repeating. Okay, now this guy, it never repeats, so that one is just a non-repeating rational number. You already wrote down natural numbers are 1, 2, 3, and so on. Whole numbers are 0, 1, 2, 3, and continuing. Integers are whole numbers and their opposites, so 0, 1, 2, and so on, and 0, -1, -2, and so on. Rational numbers can be written in the form a divided by b, where a and b are integers and b cannot equal 0. This chart is new, and it's kind of nice. It shows that all natural numbers are whole numbers. All whole numbers, which include natural numbers, are also integers, and all integers are rational numbers. And these are all subsets of real numbers. There are numbers that are not rational that we're going to see pretty soon too. So this chart would also be a good thing to have in your notes so you can see the relationship of how they connect. To graph a set of numbers means to draw or plot the points named by those numbers on the number line. The number corresponds to a point on the number line is called the coordinate of that point. Name the coordinates of the points graphed on the number line. Well, we don't need parentheses because it's not order pair. We're going to use braces. They put points at -9, -7, -6, and -3. And that's all that is. Same directions, name the coordinates of the points graphed on the number line. The bit that's new is we've got this arrow that keeps going to the right. Although only a portion of the number line is shown, the arrowheads indicate that the line and the set continue to infinity, which means they never end. So this set starts at 11, it has a beginning, and 12, 13, 14, and then we can go and so on. And not keep writing numbers for the rest of our lives. Now we get to do the graphing, so I'm going to draw a nice little number line. We need points at 0, and they're going by halves, so I'm just going to label this 1/2, 1, 3/2, that's plenty, -1/2, -1, just going the same distance both sides. And arrows because it goes forever, but the only points I need are at -1/2, 0, 1/2, and 1. Ooh, this one's going to keep going. So I've got, the smallest is, we're just going to call it what it is, -1.5. Let's go -1, -0.5, 0, 0.5, 1, 1.5, and so on. So we're going to have points at -1.5, 0, 1.5, and so on. Okay, I like to draw my arrow above and going because the number line already had arrows on it because the number line goes forever in both directions. So I want you to know that this arrow is just going to go to the right and keep going. Graph integers less than -6 or greater than or equal to 1. Okay, integers are whole numbers and they're opposites, so we're just going to want dots again. So the first integer less than -6 would be -7, then -8, -9, and arrow goes to the left. And then I want integers greater than or equal to 1. So 1 gets a dot, 2, 3, 4, and so on to the right. And again, I like making my dots kind of above the number line because I think they show up a little bit better than if they're right down there on it, where it technically should be. On a number line, 4 is 4 units from 0 on the positive direction, and -4 is 4 units from 0 in the negative direction. This number line illustrates the meaning of absolute value. The absolute value of any number n is its distance from 0 on a number line and is written as absolute value of n. And we know that absolute value of -4 is 4 because it's 4 units from 0, and absolute value of +4 is 4 because it is also 4 units from 0. Since distance cannot be less than 0, absolute values are always greater than or equal to 0. The absolute value of -5/8 is 5/8. Absolute value is absolutely always positive. The absolute value of 0.25 is 0.25. It's still positive, hasn't changed. Evaluate if y is 12, so I'm going to substitute 12 in for the y. Absolute value of 12 minus 8, 12 minus 8 is 4, plus 5. Absolute value of 4 is 4, plus 5 is 9. Very nice. A set of numbers can be graphed on a number line by drawing points. To evaluate expressions with absolute value, treat the absolute value symbols as grouping symbols and use PEMDAS.